All right, so we are going to take a look here and see how this video goes. This is our second day looking at graphing complex rational functions, and I'm a little concerned that I'm trying to squeeze in too much in this lesson here. If you watch the optional video, you at least have a background a little bit about the horizontal asymptotes, which is a new aspect we're going to be adding into our graphs. Okay, because we haven't actually graphed one of these complex things. We've just only, just talked about them. But we're going to start graphing today too, hopefully. Okay, so I'm going to go through this quickly as I can. As a review from Friday, okay, remember that we, have been talking about these excluded x values, right? These x values that we want to exclude from our possible x values, that is, exclude from the domain, right? Restrict from the domain, because sometimes x values cause us to divide by 0 in these complex, in these rational functions. Okay, so what we're going to do then is take a look here at this particular one, just as a brief, introduction here. Rational function, right? The numerator is factored, but the denominator factors to 3x minus 1 times x minus 1. Okay, like that. And so we want to see what x values make us divide by 0 here. So we set that 3x minus 1 equal to 0. We set the x minus 1 equal to 0. We solve, and we get x equals 1/3 and x equals 1. Now, the difference here is that 1/3 is a vertical asymptote at x equals 1/3. What makes that 1/3 a vertical asymptote? How can we kind of tell? Well, I mean, if you graph the function, you'll see it there, but of course we're trying to graph, so we need to know that that's a vertical asymptote. The value 1/3, if you were to imagine to plug it back into this original function here, either in the factored form or in the unfactored form here, you would end up with a non-zero number in the numerator, right? 1/3, 1/3 minus 1 would be -2/3. So you'd have -2/3, but then in the denominator, when you plug that 1/3 into here, you're going to get 0, which multiplied with this will result in 0 in the denominator anyway. So you'll get -2/3 over 0, which is undefined. All right, and that undefined idea leads us to the fact that we're going to have a vertical asymptote there at 1/3. Okay, now with 1 though, this is a hole. Why is there a hole at 1? Because if you plug 1 back into your function, again, the factored function, terrible arrow, or the original function there, okay, you'll get 0 over 0. This is not undefined. This is called indeterminate form. Okay, so that is a different result, and it results in x equaling 1, there being a hole at x equals 1, okay? Then to find the matching y coordinate, you would actually just go ahead and cancel out those x minus 1s, leaving you with 1 over 3x minus 1, and then you'd sub in 1 for the x right there, and you would get, let's see here, 3 minus 1 is, so it'd be 1/2. And so you get 1 comma 1/2 is where the hole would actually happen. You put an open circle there for that point. Now, that was the review from Friday. Now, for horizontal asymptotes, okay, there's the general way that we find horizontal asymptotes. So in general speaking, it's the end behavior of your function. That's how you find a horizontal asymptote. If the end behavior has a number that's not infinity, okay, that indicates that you have a horizontal asymptote, okay? So it's finding the end behavior. That's all it really is, okay? Now, for rational functions, there is a specific rule that we can follow. So this is only true for rational functions, what I'm about to show you here, okay? And so in summary, there's 3 different categories of rational functions we'll be considering when we look for horizontal asymptotes. There will be the example where we have a function where the degree of the numerator is less than the degree of the denominator, okay, which is this example right here that you see, okay? And in this case, the horizontal asymptote will be at y equals 0. Easy enough, okay? Horizontal asymptote, y equals 0. Okay. In the second case scenario here, this is where the degree of the numerator is equal to the degree of the denominator. And in that case, it's a little bit more complex to describe, but it's much easier to just see. If the horizontal asymptote is at y equals the ratio of the lead coefficients. So if you look back over here at our example, here are our lead coefficients. Okay. Now one thing you gotta keep an eye out for is if your numerator and denominator are written in standard form. That means highest power to next highest power to next highest, highest power to then that was actually right. So, descending order of power, kind of thing. Like this is in standard form too, okay? Just make sure your numerator and denominator are in standard form. Once we're in standard form, you look at the lead coefficients here. The numerator is 4, denominator is 1. So what's the ratio of those lead coefficients? 4 over 1, which is 4, right? So this is just 4 over 1, or just 4. Okay, so that's where our y asymptote is. Or sorry, our horizontal asymptote is at y equals 4. Or 4 equals y there. Okay. The last category possible here is for the numerator when it's greater than the denominator. Okay, so if the numerator's degree is greater than the degree of the denominator, like we have in this situation right here, well, there is no horizontal asymptote. It doesn't exist, right? If you were to, again, to imagine doing your end behavior here, how can we actually do that end behavior? Well, one way we can do it is using our graphing calculators. You know, you go to your table on your graphing calculator, you type in really, really big numbers, increasingly big numbers, and you see what y value this function approaches. It's going to go to infinity. All right. Likewise, you can approach negative infinity for the other end behavior, right? As x approaches negative infinity to the left, you can plug in smaller and smaller numbers, you know, negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000, so on and so forth. And this will go, the y values then will go to negative infinity as well, which means if they go to infinity, that there's no single number, right, that the asymptote goes to, so it doesn't have an asymptote. However, there is something called a slant asymptote, and we probably will look at that more tomorrow just because I don't want to squeeze in too much today. I'm already 6 minutes into this. So, you know, we'll maybe talk about slant asymptotes tomorrow or something like that, okay? Yeah, so let's jump into then an actual example here, okay? A slant asymptote would be just a diagonal asymptote like this. Again, we'll look at that tomorrow maybe. All right. So example, sketch the graph of the given function, identify all VA for vertical asymptote, HA for horizontal asymptote, SA for slant asymptote, we won't have any of those today, holes, x-intercept, and then the domain, and then there's also the range there too. I should probably zoom this out just a skosh. Okay, like that. So here's our function. All right, let's identify, man, tapping is not my skill here, so go away. All right, so, okay. So anyway, what's our domain here? Well, again, we can just look at this function and see that 2 is going to make us divide by 0. And so we're going to say negative infinity to 2, oops, union to infinity, right? Again, if you really want to, you know, just see the calculation here, is just x minus 2 equals 0, and so x equals 2 would be our excluded x value. So we want to exclude that from the domain there. Now, that domain restriction, right, that x equals 2 that we got, all right, that we exclude, that will either classify as a vertical asymptote or a hole. It cannot be both, right, but it will be one or the other. Now, in this case, which one is it? It's a vertical asymptote because when you plug 2 into the function here, you're going to get 3 over 0, which is undefined. And since it's undefined, that indicates we have a vertical asymptote. And that's why I want to write vertical asymptote at x equals 2. Okay, there's no more domain restrictions, right? We took care of the 2. There's no more domain restrictions, so there's no holes. Okay, so that's important to identify too. All right, so we can go ahead and draw that vertical asymptote in over here at x equals 2. So there's my vertical asymptote at x equals 2. Again, just a dotted, represent it with a dotted line. You can label it if you want to, not necessary in this case, but we're going to do it. All right, so horizontal versus slant asymptote. I told you we're not going to have any of those today, so just a horizontal asymptote. What do we do horizontal asymptotes? Well, again, it's a rational function. We go back to our little table here. Which scenario do we have? The first one, the second one, or the third one here? Well, it's the second one. The numerator's degree is 1. The denominator's degree is also 1, and so it's the lead coefficients, the ratio lead coefficients. This is in standard form here, so this is going to be 1 over 1, okay? And so that will be our horizontal asymptote here at 1. And so again, I will draw a dashed horizontal line here at 1, and again, you can label it HAY equals 1, and then our x-intercepts. Now the x-intercepts, that's when this thing is equal to 0, okay? So we want to set x plus, actually I'll do it down here, x plus 1 equal x plus 1 over x minus 2 equal to 0. Now, this is a fraction, right? This thing over here is a fraction. A fraction can only ever equal 0 when its numerator is 0. So we don't need to worry about this x minus 2 part. We can just say x plus 1 equals 0, which means then x is negative 1 will be a x-intercept. And so negative 1 right there, we're going to have a nice point, x-intercept. Okay? Finally, the range. Well, again, we can see here from our function, the only thing that our function won't probably intersect is that horizontal asymptote at 1. So we can say negative infinity to 1 union 1 to infinity, right? We're going to hit all those other values. And at this point, we can just go ahead and pick an x value to the right of our asymptote, pick an x value to the left of our asymptote, and graph it, okay? So let's see here. I'll plug in 3. So if I plug in 3, let's see, it's be 3 plus 1 over 3 minus 2. And so I get 4 over 1, or just 4. So 3, 4. 1, 2, 3, 4, right there. And I actually already have a point here, so I'm just going to use that. I'm not even going to plug in the other one. I know it's got to go through there, so it's going to look something like this. Oof. Okay. And so there's that, and then we'll do this right here, and voila, there's that one. Okay, so there's our graph. All right, I know I'm at 10 minutes, but I'm going to do this next one here real quick. All right, the next one, all right, same idea as before. We're going to find the domain, but this one we'll need to factor that denominator. So it does factor, and again, this is why we did factoring before we did rational functions, because you're going to use it here. Okay, so let's see here. X minus 4x plus 1 is what it factors to be. And ooh, look at that. They're the same thing. We'll get to that in a second here. Still, these domain restrictions are going to be at 4 and negative 1. So our domain will be negative infinity to, what's the first domain restriction we come across? Negative 1. Union, then we go from negative 1 not to infinity. What's the next domain restriction? 4. Union, then we go from 4. There's no more domain restrictions, so we go to infinity then. There's a domain. So again, this 4 and negative 1, those are going to be either vertical asymptotes or holes. Okay, we'll have a vertical asymptote at 4, because again, when I plug 4 into my function up here, either the factored version or the unfactored version, okay, it's going to result in undefined. I'll have a non-zero number divided by 0. Okay, 0 being the denominator, but not in the numerator, so that's our vertical asymptote. We're going to have a hole at negative 1, because we have that same factor in the numerator and the denominator. So we can actually kind of imagine canceling that out, leaving it 1 over x minus 4. And I can now plug that negative 1 in here and find out what the matching y value is. So if I plug negative 1 in, it'll be negative 1 minus 4, which is negative 5. And so it'll be 1, or negative 1/5 for the whole there, coordinate. Okay. Horizontal slant asymptote. Okay, so the degree in the numerator is a 1. The degree in the denominator is a 2. So the numerator's degree is smaller than the denominator's degree. So if we go up to here, numerator degree smaller than the denominator degree, that means we have a horizontal asymptote at 0. Okay, so we'll draw in that horizontal asymptote here at 0, okay, which is just the x-axis. I should also go ahead and draw in my vertical asymptote at 4. So 1, 2, 3, 4, we'll say, is right there, like that. Okay, and we have a hole at negative 1, 1/5. So let's see, I'll go ahead and put that. So negative 1 would be right there. It'd be negative 1. So negative 1, negative 1/5. I don't know, it'd be like right there. Okay. So we did the horizontal asymptote to y equals 0. And then finally, x-intercept. So we'll set this thing equal to 0. Okay, because again, an x-intercept will always have a, x-coordinate, comma, 0 for a y-coordinate. So we set this thing equal to 0, which is where the y-coordinate would be. And so, well, it's going to be when x plus 1 equals 0. Again, only this thing will only ever equal 0 when the numerator equals 0. But then we get x equals negative 1, but we already know that's a hole, so it cannot be an x-intercept, so there are no x-intercepts. Because that x equals negative 1 was already restricted from the domain. Our function cannot cross that, and so that can't be a 0. Finally, our range, again, it's going to be negative infinity to 0, union 0 to infinity, because again, we're going to exclude that asymptote behavior there. All right, so what does that leave us? Well, we have this point right here that I'm going to use to, just roughly sketch in something that looks like that. Okay. And then I'll have to pick a point over here, some x value there. So let's see, this x value that we're at is 4, so I'll go ahead and pick 5 and see what happens. So imagine plugging 5 in, I'll get, and I'll just do that up here. If I plug 5 in, I'll get 6 over, let's see, 25 minus 15 minus 4. So 6 over, let's see, 10 minus 4 is 6, so 1. Okay, that's easy, so 5, 1. And so we'll just kind of like that. Okay. So there's the graph. Give you guys your assignment here. I won't give you too many of these, maybe like 2. Okay, just try. So yeah, good luck, guys. Thanks for watching.